actually, so this is of size r, right? And this is of size y is m minus r. So it's 2rm as well. Okay? So this guy is n minus r, but we replace it with something of size m minus r. So it's really, square matrix, loosely speaking, right? And then if you compute Jacobian of phi, well, it is something like AR and an identity 0 and something here. So it's non-degenerate. So it's invertible matrix actually. Okay, so can I write here and over there? Okay, on both sides, here and over there also. Okay, yeah. So then we can apply inverse function theorem, which says, okay, if my Jacobian matrix is invertible, then I locally can consider inverse of phi, which is so namely there exist two open subsets, both containing zeros, u1 and u2, also in Rm, such that phi restricted to u1 is differ from u1 to u2, and actually I have phi inverse, right? Phi inverse which goes from u2 to u1. Okay, so for phi inverse, let us introduce more notation. So phi inverse of x, y, again, we separate into parts. And first part of phi inverse is A, and second is B. All right? And then, then I just would like to obtain some elementary conditions on A and B. So I just need to use that this is really inverse to phi. So I have x, y is the same as phi, and then apply to A of xy and B of xy. Right? So this is just phi inverse. Then for phi we had this Q and R, right? So this is actually Q of A of xy, and then B of xy. But then, so how phi works, in the second entry I have y, so I have to put here B of xy. And so I compare this entry with this entry, and I see that B of xy is just y. So B of xy is just y. And therefore phi inverse of xy is just A. So phi inverse of this is just A of xy, y. Right? Okay. And then then I would like to do also what? So I would like to compare I guess this entry and this entry, all right? So what I would like to write down is this composition. Phi inverse, okay, it's not very handy to write here, so maybe I'll just erase this. Right, so I would like to write down phi inverse and then apply f. So this is one step, right? So we would like to do something like psi f, then phi inverse. So we need to construct phi and psi. So we kind of already constructed phi and like our potential phi, right? And then we investigate how it works with f. Okay. So according to all our formulas, it is q of a x y y, and then r of a x y y. Now, I claim that this thing is x actually, because I should have to compare this entry with this, and b is y. So this is x. So this is actually something like x r tilde of x, y. So next observation is that actually r tilde should not depend on y. So let's see why this is true. We just can compute Jacobian matrix of f phi inverse, right? So it looks like this, right? So I have x, so I have here I, like identity matrix of size R. And then I have d r tilde over dy, this matrix, in this block. And then I have 0 here and something here. So it's just from this the Jacobian matrix of f composed with phi inverse looks like this. But okay, so phi is diffio, f has rank R, so we already have block which is of full rank, this identity matrix, right? So therefore this should be 0 matrix, actually. So okay, this should have rank R, right? F has rank R, composing with diffeomorphism doesn't change its rank, right? So therefore, we should have the rank of this matrix to be R. The only thing when this happens is when this is 0. And for every point, because rank is constant actually, right? So actually then dr tilde over dy is 0, and r tilde of x, y is actually just r tilde, it just, let's call it s of x. It just depends on x, doesn't depend on y. Okay, and right, so okay, let's what we have? We have phi inverse composed with f of x, y is just x, just depends on x actually, s of x. It's already very good. So we now need to make something here to make psi such that this will be 0, right? We already have dependence only on the first part, right, which is good. So now we would like to make somehow this entry 0. Okay, again, some technical requirement. I would like to take my U2, this one, right, from phi inverse goes from U2 to U1, and shrink it to make it actually cube without boundary. So let U3 inside U2 be a cube. Well, cube, I mean open cube, right, without boundary. Well, should contain 0, so containing 0. And let me denote finally my U, right, that I needed in my theorem is just phi inverse of U3. So put this. Now what would be my V? So V is all points VW in V0. V0 is n actually, right? Just to recall. Such that V0 is inside U3. So this is by definition my V. Okay, what I need to check? I need to check that f of u is inside V. That was one of my requirements for this u and V in my charts. We don't have psi yet. We're about to define it. But we have, so we have phi inverse of U3, right? And U3 is well, is a cube for some technical reason. Well, you see why we need it on this step. So phi inverse of U3 composed with F lives, so this is V, this is my V, lives inside V. Sorry, this is U, right? This is U, lives inside V. This just follows from this and the fact that U3 is cube. And so if I have V0 x as of x as x is inside, right, then x0 is inside as well. Yeah, so I claim this. This is what we needed for my u and v, right? I wanted f of u to be inside v. So that's what we'd like to see. I claim that this follows from two things. From this one and the fact that u3 is a cube, right? So everything, so if I have a point xy in the cube, then point x0 is also in this cube. So if xy is in U3, then x0 is also in U3. And so then from definition this of V, this just follows. Some technical thing, but I mean, we cannot avoid it. All right. Then I need psi. So psi I construct like this. Psi of VW, right? So psi goes from V, right, which is an element, which is subset in Rn. Again, I break it into parts. From V to where? To Rn as well. Right, from open subset of Rn to Rn, and then by definition, this is just VW minus S of V. And you see, so I would like, so V is defined in such a way that what I put in here also makes sense for S, to put it inside S of V, right? So that's all these technicalities to define psi and for f of u to be inside V. All right. And then we just need to check that, well, first of all, psi is differ on image. Onto image. Because I can present to you inverse map just explicitly. So psi inverse of S and T is just S T plus, well, S of S. So instead of minus, I have plus here. You compose to get the same thing you started with, actually. And then, which is just by construction smooth, so it's differ. All right. And then I need the composition phi inverse f and then psi to be to have the form that I needed in the theorem. Well, okay, it is psi from the construction just follows psi of x s of x, because we know that this composition just x s of x, and then we just need to apply this, right? So it will be x s of x minus s of x. So this exactly what we need. Okay, so we proved the rank theorem. It's actually, I don't know, it's actually, you need to go through some technicalities, but it gives you a lot of, if you like honestly now did this step, it gives you a lot in differential geometry in smooth manifolds.
I'll ask you once again.
Sure.
We want to show that every point x, y in U3 has an image which lies inside V.
Yes.
We say that x, y from U3 is what? It is.
Yes. So U3 is a cube inside U2.
Yes.
Containing 0. Right. Then well, we apply this to this cube.
To the point xy.
To the point xy. Get this. So this is inside U. Sorry. This is inside this image. So I would like to see that this is inside V. Yeah. Okay. So since right. So then what? Then I would like to see that x s of x, so xy is inside U3. So therefore x0 is inside U3. Then from the definition, therefore VW, so the image, right? Their image is this one, right? With x, which such that x0 inside U3. So therefore it's inside V. Yeah. Whew, okay, so now this is done. And now we can introduce a couple of notions which are important. Right, so suppose that I have, again, some smooth map, can compute its differential at points. Then we say that, so definition, if dpf is injective for all p in M, then f is called immersion. And another case of full rank is when this dpf is surjective for all p, blah blah blah. Then we call it submersion. Okay. Then third thing that is usually given name to is embedding. Yeah, by the way, Russian names are kind of, I think this is embedding is вложение, это погружение, а submersion я даже не знаю, что такое. No, immersion might not be injective. We only for well, you can take curve, right, and do it to something like this, right. This is not injective, but differential is injective.
What is the immersion here?
Well, you just take, I don't know, you take some I don't know interval, or even like a real line, and put it into like figure 8 curve. It's actually a lot of, well, to be cyclic, right? Or you can actually just take R, right, to R over Z, just without this, just to circle. It's not injective, of course, but it is an injective, but it is an immersion. Differential is injective, of course. At every point, if you consider tangent vector, it goes to some tangent vector, non-zero tangent vector on the circle. Okay. It is actually immersion and submersion, both, this one, but not a diffeomorphism. It is a local diffeomorphism. Right? Locally, if you take like something on R, that goes locally like diffeomorphically to the circle. Okay, then let's talk about submanifolds. So this is usually what should be discussed, because there are different notions of submanifolds. Our definition is like this. So let M be a smooth manifold, and then let me consider N inside M. First of all, it's just subset. It's the topological space itself, but maybe not in the subspace topology of M. So M is a manifold, actually. I even need more from it. So M is a manifold, but important remark here is that topology on N might not be subset topology. Okay. This is set up, so I didn't give a definition yet. Then N is called an immersed submanifold submanifold if the inclusion map is well, injective immersion of, well, of course it's injective, is N immersion. So injective immersion. This is the definition. And this is one type of submanifold, another type of submanifold. So this is maybe like this. So if additionally well, I is homeo to the image, which is the same as N has subset topology. Right? All the open sets of N are given by intersection of open sets of M with N. Then N is called embedded submanifold for obvious reasons. And usually when we just say submanifold, well, in different books they have different conventions, but when we say submanifold, we mean, for this class at least, we need we mean embedded submanifold. Okay, so the classic example, right, of something which is immersed submanifold but not embedded is a figure 8 curve. So you take open interval, right, and map it to R2 as follows. So you take something like this, right, where these open ends, they come like infinitely close to the origin. And you say, okay, this is manifold, and manifold structure comes just from the interval. But and this map from interval to R2 is injective immersion. Injective because, well, this point is only in here. And then, but this is not a subspace topology, right? Because we have trouble in this point, right? In subspace topology, if I try to, consider open sets, open neighborhoods of this point, in the pre-image they always will look like this. Something here, and something here, right? But here we also have open neighborhoods of 0 without these endpoints, which never happens in subset topology. So therefore, this is not a homeomorphism to the image. Okay. Another standard example, which is harder to draw, but it's irrational winding of torus. It's more related to, Lie groups. It's standard example of Lie subgroup, which is not a Lie subgroup in some terminology of some books, but like a virtual Lie subgroup. So it's not a submanifold, but rather immersed submanifold. Okay. Well, why do we care too much about this technicalities? Yeah, because we actually need both in the theory, and they both useful from different points of view. For example, embedded submanifold, well, you can obtain chars on embedded submanifold from chars of bigger manifold. Just in usual way, you just take chart and intersect, and this will be chart and submanifold, which is not true for immersed. But immersed you need for studying images of smooth maps. So image of smooth map is not might not be submanifold, but an immersed submanifold. And that's also another important thing. Okay. So we would like to see how we can now say that our immersed our set actually is a submanifold. Okay, again, let n of m be a subset, just subset, and m is smooth manifold. We say that n satisfies k-slice condition if for every p in n there exists smooth chart of m such that, well, chart around P, of course, such that n in locally in this chart, so n intersect U, and if I apply phi to it, is just all looks as follows. It just looks as slice of my of the image of phi of u by subspace of dimension k. Right. So x1, x2, blah blah blah, x. I don't know what should be dimension of M is M, such that, so from Rm, such that x k plus 1 and x k plus 2 and so on equals to 0. So this is what's called k-slice. Okay, and so we have actually a theorem which is corollary to the rank theorem that says that that actually there's an equivalent definition of embedded submanifold using this local well, just case-wise condition. So suppose that n is suppose that M is k-dimensional submanifold of some manifold M, then it satisfies case-wise condition, and conversely, if I have a subset which satisfies case-wise condition, so conversely, if n set M is a subset satisfies case-wise condition, then n is embedded submanifold of dimension k. Well, that's of course so correct spelling would be then on n. Well, then in subset topology, right? On n I have smooth structure such that n is an embedded submanifold of k. Right? So this theorem is good because I started with just some set with some property, right? Without even structure of immersed submanifold, right? And then this gives you embedded submanifold. Okay, so proof is easy once we proved the rank theorem. Okay, we suppose, well, which direction? First this one. So suppose n is submanifold, then
right now, does the word submanifold mean embedded?
Embedded, yeah. Yeah. Always when I don't say anything before submanifold, it means embedded. Right, so n is submanifold. Then we just apply rank theorem to the inclusion map. So inclusion is injective immersion, which is, well, inclusion is embedding, right? Just from our definition of embedding. In particular, it's smooth. In particular, it is smooth map, so of well, the rank of this map is constant, right? Because well, if you have some tangent vector, right, then di brings you to tangent. Well, it's just immersion, so it's constant rank. And then I can apply smooth the rank theorem to it, and well, then I have this map, well, charts, right? U phi and V psi, right? This is chart of M. This is chart of N, such that well, I phi inverse psi of x1, x k, and so on, x m, right, is just, well, in this case, it's just x1, xk. So this is just application of rank theorem. But then, right, so no, I think I need what? I need to do x1, sorry, I need to do like this, right? Because this should be chart. So I from n to m, right? It's kind of a little bit switched from the rank theorem, right? Because in rank theorem we had from m to n, right? So this should be chart of n and this of m, right? And then I take this x1 through xk and map it to this. That's what we need. And well, here I have how many zeros? M minus k. So this is what rank theorem says. But also, this is, now we need to use that this is actually, so that we have subspace topology of n. Right? And so I have U is open in subspace topology. That's where we use that it is actually embedding, but not in just injective immersion. So therefore, my U is just V0 intersect N, right? And then, well, I need, okay, and so U is a V0 intersect N. So we would like to have some chart right here, which satisfies Slice condition. That's our goal, right? So we would like to take. So we have this V0, right? And we have V. So we take V1, which is V intersect V0. So then, actually, V1 and then psi restricted to V1 is the chart that we need for k-slice condition. Okay. That's I just don't want. So okay, we had some details in rank theorem, right? I just claim that this is true, and this is few more technical steps to actually see this. So let me just leave it like that. All right. So what we do, I can draw a cartoon. So I have n, right, that intersects, and so I have, I have, this u, right, which is part of this n that is intersected by this v, right? But then what can happen is that actually somehow n goes and intersect my v somewhere here as well. Maybe I don't need this line, so let's draw. So in my picture m is 2-dimensional, n is 1-dimensional, right? So this is v, this part is u, right? But what can happen is that actually I take v big enough such that another part of n actually intersects this, right? Then making this intersection actually shrinks it so that actually I have something like this, and piece of my v is exactly so this is v1, right? Piece of my v is exactly case lies in v1. This cartoon, okay, if I go through all the details, then we'll be just stuck. Okay, not stuck. It's much simpler. It's just we have spent I guess too many time for this. And then conversely. I need what? If I have case-wise condition, right? So conversely, suppose n satisfies case-wise condition, then what? Then I have if I choose point P, right, then I have this neighborhood in the chart, right, such that phi P of u P intersect n looks like we need, right, x1 blah 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 x k 0 0 0. This is just a case-wise condition, but then it's clear. Then if I just I just can define my atlas as follows. It's just these pairs u p intersect n, right, and phi p, restricted to this. As p, I can just run p over the whole n. So this is, I claim that this is smooth atlas, of course, right? Because smoothness of coordinates just come from the smoothness of coordinates on M. And that's it. So this is smooth atlas. And that's it. So we really used we really used rank theorem, and this is smooth atlas, right? But embedding N is an embedded submanifold just because in this case, we chose submanifold topology. So this is embedded just by definition. Right. So right, because this is in subspace topology, right? This is open neighborhood. That's where we used it. Right. So we take subspace topology, and then I claim that this is atlas. If we didn't start with subspace topology, that wouldn't be open neighborhood, right? So and the fact that we started with subspace topology by construction gives us embedded, not immersed submanifold here. Okay. Any questions? Right. So let's continue our story. So let's have couple of corollaries coming from this theorem. Okay. Corollary 1 is that if N is a subset of smooth manifold N, then it has at most one smooth structure such that N is a submanifold of M. Yes. Well, this is clear, right? It is corollary rather to the proof. Well, so suppose that I have two different smooth structures on N that make it such that it's embedded, right? Then I apply this case-wise condition, right? And then I have that this case-wise charts give me a smooth atlas, and for both smooth structures. So actually the same atlas, which is smooth for both smooth structures, so they actually coincide. Right, so this construction of case-wise gives you smooth atlas for any submanifold of M. So if you have two different, then the smooth structure should coincide. Well, okay, this is just, natural question to ask.
You say that it has at most one, it can have zero?
Sure, you can pick some very crazy subset which does not satisfy case-wise condition, for example. Right? Which has zero chance to be submanifold, of course. All right, so corollary 2, which is very useful and is used in other areas that need differential geometry, is its constant rank level set theorem. It says if I have a smooth map smooth of constant rank then F inverse of P is submanifold of M for any P from N. So fiber of any point is actually submanifold if you have a smooth map of constant rank. And proof is clear. You just apply what? Well, you apply rank theorem, right? Which gives you that. So apply rank theorem. Which actually says that that F inverse of P satisfies K-slice condition, or whatever, R slice, right? Condition. Actually, I can say even more. I can say, so this is smooth of constant rank, let's say R. Then this is submanifold of M of codimension equals rank of F. Right? So, which is R. And just rank theorem says that this exactly says for our map that F inverse of P, right? This is exactly the slice. The slice in coordinates looks like a R slice. It's exactly rank theorem, and therefore, by what we proved before, it is submanifold. Mm-hmm. Ну, давайте посмотрим. Вот у меня, допустим, есть две структуры гладкие. Да, и в этих гладких структурах n у меня под многообразие в m. Вот. Тогда я, тогда я просто применяю конструкцию вот этого K-slice, вот, и говорю, что и в той, и в другой гладкой структуре вот такой атлас — это гладкий атлас. Но так, если эти две структуры имеют один и тот же, ну, общий гладкий атлас, то они совпадают.
Почему он в обеих структурах гладкий атлас?
Ну, потому что у меня есть вот это условие вот этого K-слайса, да, K-сечения. Ну, значит, ну просто потому что, ну, что оно говорит? Что вот у меня вокруг каждой точки есть вот такое, да? Да, вот в каждой точке у меня есть такое, и сейчас.
Если я для каждой точки возьму другое и то почему гладкая структура не меняется?
Ну, вы можете как бы другие координаты взять, типа там x, там x в кубе, как мы там рассматривали, да? Но тогда это будут другие гладкие координаты для m. Понимаете, да? То есть они именно пришли с объемлющего пространства. Мгм. То есть и в том, и в другом случае вот ваши координаты, они пришли с объемлющего пространства. Окей. So, yeah, guess we don't have non-Russian speakers today, but I don't know, maybe they watch TV. So we'll continue. All right. So we have this corollary, and this is used, for example, I don't know. This is a good theorem. So when you consider the actions of Lie groups on manifolds, right? So divisors of actions usually give you Lie subgroup. And it's a very powerful theorem. And this is this corollary, because well, you just proved that certain map there has constant rank, and that's it. Okay, what? Okay. So we have a version of this corollary, which involves so-called notion of so-called regular value. So let me erase this. Okay, so again, so suppose I have smooth map. So this is a definition. So smooth, and suppose that, well, then P is from M is called regular point, if differential at this point is surjective. On the other hand, if I take point in Q in N, so Q from N is called regular value if pre-image consists of regular points. Of regular points. Yes, and so corollary. Let's see. Corollary. Three says that if Q is regular value of F, then again there exists smooth structure on F inverse of Q, so such that it is embedded submanifold. So I'll just write on a board that then F inverse of Q is submanifold of M. Okay. what do we have? How to prove this? Well, we need one additional observation, is that if I denote by U the set of all regular points of F, so of M, well, so all regular points of F, right? But these regular points live in M. So P is regular point of F. So I claim that U is open in M. Well, why this is true? Okay, so so if I have no regular points at all, then it is empty, so it's open, it's okay, right? So if I have at least one, so let me take, so suppose that I have some P in U. This means what? This means that D, well, so it's surjective, right? And suppose that, regular value, so differential is surjective, right? So it's a full rank, and suppose that so it's from M to N, right? And suppose the dimension of N is N small, right? Then yeah, I have some N by N submatrix of DPF, which is not degenerate, which is non-degenerate. Of course, in some chosen coordinates, but whatever. Non-degenerate. And so entries of this matrix depend on P continuously. So entries of this matrix depend on P continuously. And so I have condition, right? So that at P, like determinant of this n by n matrix is not 0, right? Then by continuity, I have some neighborhood around this point, such that for each q from this neighborhood, determinant of this n by n matrix is not 0, right? So people say it's open condition, right? So something is not 0. It means that it happens around, if I have continuous dependence on something, it happens around this point, like in a small neighborhood of this point as well. Okay. And so therefore, for Q close to P, this n by n matrix So, or I should say dq, my dq f also has n by n matrix, which is non-degenerate. Right, and so if I have a regular point, then around this regular point, all my points are also regular. Very well. On the other hand, if so I have F inverse. Well, Q is not good because I fix it over there. So maybe P tilde, right, close to P. Right, Q is rather in our notation a point in N. So then this is, well, it lives inside U because Q is regular value, right? Therefore, everything in the pre-image is regular point on the one hand. On the other hand, if I take F so F and restricted to U, this will be a map of constant rank. So it's of constant rank. Which is n, right? Which is dimension of n. For each regular value, my rank of the differential is the full one. Okay, and moreover, since U is open, it is submanifold of M. Right? Open subset of a manifold is also it is also manifold and actually submanifold, right? So U is submanifold.
Why is it not, if it's open, it's a
Sorry, say it again.
Why is that if U is open, it's submanifold?
Well, just because you take any point and you make your chart small enough to fit in this in this open neighborhood, right? And this will be a chart for your open. So you just take your U, right? So let me draw a picture here. You take a point inside. So U lives inside something bigger, M. And then you have charts for M, right? So charts for this around this point is something right here. So just restrict it to be like intersected with U, right? An intersection of this V with U, and the map that maps from this intersection gives you the chart. Of course, all this happens in subspace topology, so it's really embedded submanifold. Okay, so U is submanifold. F inverse of Q is inside U. This is of constant rank, so we apply constant rank theorem. And we know that F inverse of Q is submanifold of U. So if I have like a chain of submanifolds, right, then it's kind of transitive, right? If I have M1 submanifold of M2, and M2 is submanifold of M3, then M1 is submanifold of M3, actually, right? And so this is, so therefore F inverse of Q is submanifold of M. Okay. Right. So this actually gives you this actually gives you very well tool how to see if something is smooth or not. For example, in algebraic geometry, right? So you might have smooth algebraic varieties, right, given by zero sets of polynomials. But you might have also some self-intersections, say. And so how to check that this doesn't happen? Well, you just take your polynomials that are given in the definition of your variety and compute differential at just for general point, right? And you can see, if you see that it is surjective, right, then actually you just need, okay, so you just need your differential to be surjective you need zero to be regular value, right, of your polynomials, right, that define for you your variety, right? And this is actually pretty easy to check usually. And I have an example here, but which is just almost trivial one, but I don't have time for it. Okay, so let's finish at this point the lecture. Have a break, 5 minutes, and then proceed to seminar.
Вот я какую-то задачу решал, вот как их нести или как или отметить.
Сейчас,
На это семинаре.
да, будет, значит, листик такой,
И там
и вы просто должны написать, что вы там готовы рассказать там какую-то.
это еще надо вносить? Вы говорили.
Ну вообще в Google класс надо загрузить, да, там ссылка, в принципе, да.
А можно вопрос по первой лекции?
Да, хорошо.
Там про коциклы.
Ага.
Не дублирует же его. Вот. Вот. Я не поняла, ну то есть вот коцикл, он же откуда? Он из пересечения
Да.
в ЖРК, да?
Да.
Тогда я не понимаю, что значит вот эти условия, потому что вот это отображение отсюда сюда, а это отображение отсюда сюда. Сейчас нет, наоборот, отсюда сюда тоже.
Да, вот это значит, это не обратное отображение, это взятие обратного линии, уже это как бы префиксированные точки здесь. Вы рассматриваете линейное отображение, которое получается, и его обращаете линейно. Обратную матрицу просто берете.
Ага, то есть это все история при умножении матриц, которые получаются.
Да, совершенно верно.
Хорошо, спасибо.
что решили по поводу записи семинаров? Их нужно записывать или нет?
Ну вот они записываются.
Хорошо.
Да. Единственное, что я не знаю, какое качество там будет, потому что люди забывают надевать там микрофон, там всякое такое. Ну, как бы то, что на доске видно.
Ну, лекции планируется записывать.
Не, ну лекции, ну нет, и то, и другое планируется записывать. Просто у нас семинары такие специфические, это не один человек разговаривает у доски, а скорее каждый, и каждому надевать микрофон обычно как-то забывают люди. А сегодня первый уже, да? Уже. Так, давайте я опущу листик. Листик. everybody sign. Okay, we still have this.
А кто еще не подписал?
Может быть, более современно это как-то делать. Какой-нибудь доступ к Google таблице в Телеграме, например.
Очень много людей.
Да?
Много людей, я думаю.
Ну да, действительно. Обычно эта система работала для случаев, когда поменьше народу.
Google таблицы тогда будут записываться люди, которые могут быть пришли.
Да.
В этом проблема. Но это можно просто заранее терминировать.
Нужно просто какое-нибудь серьезное доказание, если вдруг кого-то вызвали, а человек... Не, ну я не знаю. Ладно, можно и так. Пошел. Значит. Ну давайте, окей, запись уже идет, да? Она вместо нас есть. Okay, so if you are okay when you present a problem, if you're okay with that, when I want to ask you to don't forget about microphone. I don't know. Maybe it would be useful for somebody, maybe not. I don't know. All right, so let's start with number one then. Okay, maybe Matvey, may I ask? Ну, если вы не против.
Да.
Вроде в прошлый раз на записи, вообще говоря, даже учитель слово «лежа» было слышно.
Было слышно, да?
Ну вот. Так, да?
Ну, посмотрим, если мы берем слишком много времени тратить на нормальный микрофон.
Первая задача была про век CP1, да? Вот. И еще был про RP1, да? Вопрос. Ну, я начну с RP1. Вот. Значит, на английском говорить лучше, да?
Ну и да.
Okay. So, we know that RP1 is diffeomorphic to S1, yeah? And the tangent bundle of S1 is isomorphic to trivial bundle. Yeah.
That we know, for example, from previous list.
Yeah. So, the sections of these trivial bundles are задаются, sets, defines by a function from S1 to this product and defines by a smooth map from S1 to R. And this map can be identified with 2 pi periodic smooth functions on R. So this vector space is not finite generated. What about CP1? Here we have a complex structure. It consists of two charts and maps. Here U0 is pairs Z1, Z0, Z1, such that Z0 is not equals to 0. And U1 of pairs Z0, Z1, where Z1 is not equals 0. And here we set Z1 divided by Z0, and here Z0 divided by Z1. And we can easily see that transition map is Z1 over Z from this chart to this chart on the intersection. Yeah, and this is this is defined on C without 0 to C without 0. So it is a galomorphic function. Since 0 isn't here.
0 is not in... because it's an intersection
Yes.
of two charts.
Since it is intersection, we have a galomorphic function. So it is a complex manifold. Okay, the tangent bundle of CP1 can be now it is canonically a complex bundle, since each fiber is R2 can be identified with C. So it's naturally a complex bundle, and its section can be identified with function f at z if we set some chart, for example U0. So
So is it trivial, by the way? Just a quick question. TCP1?
no, since CP1 is sphere. Yeah.
Just two, right?
So we have two functions, one on U0 and one on U1. And this function sets our vector fields.
No, they should be related somehow.
Yeah. On the intersections we have such property. So G in the point 1 over Z is differential of transition map, which is viewed as a complex linear function on как будет применить?
Applied?
Applied to f at z. And it is minus 1 over z square over f at z. So g at z, w, ну, new coordinate here, it's f at 1 over w minus over, yeah. So And we know that G must be a galomorphic function. And if we consider a Taylor series of G, and since this one, we know the Taylor series of F, galomorphic Taylor series for complex functions. And
Well, the main point here, right, that all homomorphic functions are analytic.
yeah,
That was what was lacking in real world, right?
yeah. So here we can see that we put 1 over W to Taylor series of F and multiply it by W square. And this function can be galomorphic if and only if F at W, no, F at Z is alpha plus beta Z plus gamma Z square. Since in other cases we have a pole here. So our vector field can be defined by 3 numbers, alpha, beta, and gamma. So vector CP1 has dimension 3 over C.
Yeah, okay. So it's kind of little generalization of the fact that the only homomorphic the only globally homomorphic function in CP1 is constant.
Yes.
Right, but here you have differential, right?
Mm-hmm.
Which spits out as omega squared.
Yes.
Which actually compensates for some powers that you can add.
Yes.
Right, and that's the idea.
Mm-hmm.
I have a question. So
Здесь? Ну, чтобы поменять, вот это координатное представление векторного поля, да, в одной карте, а вот здесь вот мы применяем к нему дифференциал функции перехода. Вот только вот там он был в точке z, а попадаем мы в точку 1 делить на z. Вот. Вот эта штука, то есть мы просто дифференциал матрицу Якоби применяем, но в данном случае это просто умножение на комплексную производную. Вот. Комплексная производная минус 1 делить на z квадрат. Вот.
Можно еще про это думать, как там касательное расслоение сдавалось через коциклы. Вот оно в этом случае это 1 на 1 матрица, да, которая коцикл.
Ну да, да.
Okay, we have to switch to so my question is that, okay, you showed that T(S1) is infinite dimension, but over R.
Mm-hmm.
But actually, is that true for any? So any real vector space on any manifold, is it infinite dimensional?
Еще раз.
Over R. So if you take vec x, where x is real,
Ага. Так.
is it infinite dimensional over R, or might be finite
if x is point,
So if x is then it is it's zero dimensional.
yes.
Otherwise, if not point, okay.
I think it is infinite dimensional since the main point we have that if we have some vector field on the some open set, yes, or some function on the open set, then there are infinitely many. Как будет продолжение? Extensions, yeah. There may be infinitely smooth extensions. But in a galomorphic case, every galomorphic function is defined on the really much more smaller sets, on countable and
Yeah, so if they
the
coincide on actually accumulation of points, right?
Yes.
They coincide for holomorphic case.
yeah, and so there are so many extensions. And in smooth case, so many.
Well, you can do this argument. You can remember that we have like this f of t, which is e to the negative 1 over t. If t is
Yeah, we have partial of unity, yeah?
Yeah, so you can if you have your manifold, right? You can take like infinite number of neighborhoods which do not intersect actually, right? And your vector field will be supported only on this.
Yeah,
right?
by,
And they are
by the
all
partial
linearly
infinity.
independent, of course, because they all supported in disjoint subsets, right? And this is the function how you can make, right? Out of this function you can make something like this, right?
Yeah, so you can extend every smooth object from some open set to
Yes.
whole manifold.
So this will be supported only in here, right? So you can-
Yes.
Okay, thank you. Any comments? Questions? Alright. So let's now do number 2 then. Yeah, thank you. Number 2. I don't know.
Ask one question about why can't we take the vector field like minus y, minus yx. It is its tangents in real case. It is tangent to the circle, and so we can consider it as a vector field on an RP1. But why is CP1 cannot be trivialized in the same way?
Can you write down what particular Yeah, so you take an RP1.
Потому что это сопряжение. А это не головоломка.
Или зависит от угла как.
Там построилась точка x, y. Это минус y плюс. В вещественном случае на окружности неизвестно задает вот такой типа поле, который касается окружности. Реально.
А как вы сделаете в S2? У вас нету...
Нет, не вызываю.
У вас...
с этим и CP1.
Ну, CP1 это S2, в том-то и дело.
Ну, я хотел сделать минус, пытаться отсюда из такого уменьшить на CP2 и...
Сейчас, это в C2 что-то живет, да?
Да, это живет в C2. Ну, соответственно, такое поле при переходе. Сейчас.
Просто вы хотите CP1 куда-то вложить, чтобы...
Да, я хочу соответственно, взять проекцию из CS1 в CP1, которая, которая снова Z1, Z2 переводит просто Z1, Z2.
А Z1, Z2 лежат на окружности?
Да, они лежат здесь, естественно.
И какое условие на эквивалентность?
Ну, в смысле, вот эта точка приходит сюда.
Ну тогда вам не надо вообще C даже писать, да?
Да. Ну вот да, мне казалось, что это векторное поле, оно как бы в любом. В естественном случае мы можем сделать такое векторное поле, которое всего касается. У нас дается вот такой формул. Значит, все точки x, y у нас минус y, x. У меня вопрос, почему в комплексном случае, если мы запишем точно такую же формулу, то это не будет векторным полем, которое будет везде касаться, и которое будет нигде не нужно.
Я не до конца понял все-таки, как вы эту формулу будете писать. Здесь у вас вложение, здесь у вас вложение S1 в R2, правильно?
Да.
Хорошо. А как вы, значит, S2, куда вы хотите вкладывать? Ну, вы говорите, что вы хотите...
Я хочу смотреть как CS1. CS1 вложить в C2.
CS1, еще раз, это значит Z1, Z2, которые обе лежат на окружности.
Ну, у которых сумма квадратов равна единице, у которых сумма квадратов модуля равна единице. Там в комплексном случае нет окружности, нет сферы. Да, нет окружности.
Не, ну вы можете сказать, что Z1 по модулю равняется единице, Z2 по модулю равняется единице. Но правда это уже не гламурно, если у вас абсолютно...
Я понял, хорошо. То есть там в комплексном случае нет гладкой.
Ну, если вы просто выделяете как бы абсолютно модуль,
это же S3.
ну и да. Ну, просто надо, если вы говорите, что есть конкретные формулы, то вы можете их записать. Если они используют абсолютное значение z, то это уже что-то не гламурное.
Понял.
На вторую задачу Мария Ильинская.
Ну, значит, вторая задача заключалась в следующем. Берется коммутатор двух векторных полей. Нужно доказать, что это тоже векторное поле, и найти его в координатах.
А вам по-английски не очень, да?
I will try.
Okay.
So we have this, and we have to prove that it is a vector field and find it in the given coordinates. I will work with coordinates from second one. So let x be sum of fi when we apply Что? Yes, thank you. So when we apply this is a differential operator that applies y to a function and then applies x to what we get. So what happens when we apply x to y applied to something? We have a sum of x applied to gi d over dxi. So it is the sum of fi d over dxi applied to gj d over dxj. So we have what do we do when we apply a differential operator to a product? We have to break it down into two слагаемые, забыла как. Terms, yeah, thank you. So this doesn't change. And then we have yeah, thank you. Now I will write the same formula for y applied to x applied to something. Yes, yes. When I subtract this from this, these terms, they go away. So what do I have left? I have
Which already proves that the result is vector field.
yes, yes. So I have sum over I and j fi dj j. So this is the differential operator, the vector field that we have as a result.
Okay. Okay, so we're moving faster than last time, which is good. Right. So number three. What was number three, by the way? This one is actually interesting. Окей, трошки не даю. The only one.
So let us recall the statement. We have a submersion of manifolds and we are given some vector field on M. And we are asking if there exists such a vector field on M such that okay, and the statement is this
Up to definition of what is DF, but I guess we all know what it is. Yeah.
okay.
Yeah.
I mean, maybe I could write this at every
So
point.
just apply df to each fiber, right? And maybe f of p, yf of yeah, and yf of p.
Uh-huh.
Yes, that's more explicit. Yes.
Okay, and this is equivalent that for every vertical field where the commutator is also vertical. And vertical fields are such that df of Vp vanishes identically.
It's actually another definition.
Okay.
Can you explain how they...
Okay. So I will okay, unfortunately I wasn't present at last two lectures, so I mean I just don't know if we have introduced the inverse function theorem and like explicit local forms of submersion. Okay. Okay, so the statement is that at every point P in M and its image, we can find a neighborhood Ux of P and a neighborhood Wxy. I will explain the subscripts in a bit. No, this is of the image. This is okay. So this projects here by f restricted to V, and we also have a projection from Ux times such as the diagram commutes.
Yes, this is the rank theorem actually. Right?
Okay, yeah, so is it clear? So we can find a coordinate neighborhood of the image and some coordinates in fibers locally, such that a neighborhood of point in the source is just a product neighborhood.
Yeah, so this is another description of rank theorem that we had that we formulated last time and proved this time. Yeah.
Okay. And so
only it's still not clear what are x and y.
okay, these are just references to coordinates. So we just say that we have in Ux, we have coordinates, say, x1, xn, and in Vy, we have coordinates like this. And then f in these coordinates is given by x, y.
I think y is, you have y is n minus n.
Okay, if we want to denote the dimensions by respective letters, then yes, it is true. Okay, so like that. And consequently, we have df. It maps a vector, tangent vector, d over dxi to d over dxi downstairs, and it maps tangent vector. Okay.
So the image of df is
Okay, is zero, okay, is zero.
So the image of df is actually gives you tangent space to fiber.
The kernel.
The kernel of the tangent, kernel of df is tangent space to fiber, which makes sense, right? Because f just contract the whole fiber to one point.
Like okay, maybe like that. Okay, this should be right. So we have like image of P, we take its pre-image, which is a fiber containing P, and we take the tangent space at P to its fiber. Okay. And now, what does it mean that for the field X, so let us write X as the sum over Y, xy d over dxy, plus sum over yj d over dyj. So what does it mean that for X, locally in this neighborhood, there exists an f-related vector field y that we were looking for? In fact, this means that these functions xy are independent of the y coordinates. So it means that d over dyj of xy. Okay, is it clear? Okay.
Yeah, and by the way, in this line, the kernel dfp equals blah blah blah, you can replace p by any point in the fiber actually.
Of course. We take p to be an arbitrary point in this product neighborhood now. Okay. And now we reformulate this condition. So
it's really what's written over the df.
Okay, what I can erase? Can I erase this? Okay, and so we have V. It is a vertical field. That means it is sum over k, v k d over dy k. And what is Vx? So by the formula before, this would be Okay, yes, yes. But actually these terms don't matter anyway because they don't prevent the field from being vertical. That's the point. So we want this field to be vertical,
Right.
which means that this term vanish
Right.
for every choice of function vk, vi here.
So this means that.
So we can set, maybe on a smaller neighborhood, we can set them to be just 1, and this will hold in particular. And that gives us precisely that. So the coefficients in front of d over dxj in the commutator vanish for all v if and only if these derivatives are identically 0, which is the condition we wanted. Okay, I think this finishes the proof.
No, wait.
So maybe this proves we should think in what direction we proved.
Wait, this finishes a proof of what?
This finishes a proof that we have reformulated the condition that the commutator is vertical explicitly in form of the coordinates.
Yes.
And we have formulated the conditions that there exists an F-related vector field. I can explain this maybe moment a bit, but we have seen that these conditions, when written explicitly like that, are equivalent.
But not clear where did you use existence of vector?
I have explained this before. So look again. Consider this vector field.
Yes.
And
So
we,
you need existence. So you need existence of what? So you have x. Yes, and you need existence of y. So here it's just only x.
no, x is a given vector field.
Yes.
And we want to see if there exists y.
Yes.
So, like, what can prevent y from existing? We compute images of tangent vector at different points of the fiber, and we might get different vector fields on the base.
Okay, yeah, conceptually that's what
Yes,
might
but
be wrong, yes.
but if we have the same all tangents vectors of x at all points of fiber have the same images, then there exists an F-related vector field. We just set.
Can you give a formula?
Okay, well, it is given simply by this formula. So, y, yeah, okay, maybe this is not visible on camera.
No, it's okay.
Okay, so y is just sum x, y of fp. And we see this just doesn't have to depend on p. And if this doesn't depend on the point in the fiber, which means in this local form, these functions do not depend on y coordinates. Then this,
And
this is
you use connectivity of fibers, right?
True, of course.
So
Yes.
because you might have piecewise constant axes, but they still different on
Of course.
components of a fiber. Then you still don't know which one to take.
Of course. Because we only work locally here, so we can't possibly see what happens in different connected components. Okay. But so this is precisely the condition that in each connected component, the functions, the components xy do not depend on the y coordinates.
So this is condition for well-definedness of y.
Of well-definedness of
Y.
functions
Of your vector field.
y, yes.
Yes. Okay. All right. Everybody follow. Right. So let me draw a cartoon. Like to draw cartoons. So this is what direction. If you have this condition that the bracket that vertical is vertical, then there exists field y.
Well, I think this proves it in both conditions. So we have proved that, assuming that, again, the fibers are connected, we have proved that the existence of F-related field on the base is equal to this condition.
Right.
And we have seen from this formula that the fact that commutator is a vertical field is equivalent to these terms vanishing. But these terms vanish for every function of vi because this is just linear in vi. So
Okay, right. So let me draw. Let me draw a cartoon then. Where maybe here. So what's going on? So we have base, right? And something which is going on so this is f is from m to n, right? So this is n, and this is like m. And so what happens is that, okay, let me fix a point, and I have a vector field on n, right? And I need to define the vector field on n. So I have a whole bunch of points on the top of this point. And a whole bunch of vectors, so I can fix point here. This will be some vector like this, right? If I fix point here, maybe something like this. So in a sense, I want to, project all of them to here and get the same vector, right? And the fact that I can use, so commutators called me derivative for a reason, right? It kind of measures how my vector changes if I move it a little bit along the fiber. So it's actually, it doesn't, so what the condition says that it doesn't change as I move it a little bit along the fiber, right? So it doesn't turn, and actually as I go, right, it's always in kind of in the same direction.
well, it might change, but it changes only in the direction that gets mapped to 0.
Yes, exactly. Well, in this cartoon it's
Okay,
hard to,
okay.
but I actually kind of can define them from any point, and it will not depend, right? It will not see this change. What could happen if fiber was not connected, right? For example, well, I have this, right, and then here. I could have like a piecewise constant coordinates, right? And here I could have something like this. And then I don't know which one I should take, this vector or this vector to define this one, right? But still it's connected, it doesn't happen. So that's the cartoon for you.
There's a condition that they say the yj is equal to 0. Is it true that it is actually the same if we take 2 points in fiber and we act just right? My question, is it equivalent to so if you take 2 points in one fiber, f of p equals f of p tilde.
You just need to be accurate if dpf and dp tilde have the same domain, right? Do they? So f is from tangent space of a point in a fiber, right? And then the tangent space of f of p, which is the same. Yes, okay, yeah, they have this, yeah, this makes sense. To write this equality. Right, and you're asking whether this condition is the same as this.
May I comment? This is the same we have been trying to say actually before. The
this condition means that locally it is true.
Yeah.
Yes. If it's connected, so we can expand it to the whole file.
Mhm.
Okay.
So this is something is constant, right? Which is locally means that yeah, derivative. Давай, да. Напомните, как вас зовут?
Поляков Александр.
А, хорошо.
So we have a vector field. And a map. We should notice that it is actually a map to to one of the charts on RP2. So we have a classical atlas in RP2. It is VI. VI is R2, and VI is I'll write like this. So like this. So our function maps R2 in one of the charts. We can call it the AQ1. And we can, using the transition functions between charts, we can compute the vector field in the other charts. So it will be a vector field on RP2 which is actually related to this field. And at first we computed with the first transition. We can write it like this. So where this and these are the coordinates in R2. So then we write a transition. And we computed inverse to put it later in the differential of this map.
So your F is this map that is.
Is this map, yes. So here it's a bit tautological. I assigned for this value x in the R2, which is u1, and y here. So the function of x, y will be these functions, and they will be equal to these values in RP2. And I compute the inverse. For instance, these are u and v, and there will be 1 over v and u over v, and this is inverse. Then I compute the differential of this map, and this is df minus y over dx squared. Then I define the differential using the inverse function to write it in the coordinates of the image, and this will be df of u and v equal to minus uv v minus 2v squared. Then we move. Then we define this vector field in the uv coordinates and apply the differential in uv coordinates to the vector field in u coordinates and obtain a vector field in the coordinates of the chart u2. Why it is a new vector field in u chart, uv u1 over v, v over v1, and we can write it as a coordinates as a vector in the coordinates of these basis vectors and apply this matrix. So this will be FUV applied to this vector, and
so you need to write this as a column vector, right?
yes. And we get u squared plus and so this is this vector field in U2, and the same transition we should apply to U3, where the transition functions from U1 to U3 will be the following. Here we have
Basically, what we're checking here is that we don't get poles, right?
yes.
And then if we apply all the transformations, right, then we in other charts we don't have poles.
Yes, and it is defined on all domain of on all the domain of U2, and we will get this is the vector field on U2, and we have the similar expression for the vector field on the U3, and we will say that it is the vector field on the whole RP2. For this map, I will state only the functions and then the vector field that is resulting, because the strategy of finding it is completely the same. And finally, the vector field y over 3 this is the vector field that we got on U3, and this is all the problem.
All right. So let's do number 5. Number 5. So maybe Reshin Kirill.
So we need to construct a vector field on a sphere which is degenerate only in one point. So we can take the coordinates, local coordinates corresponding to the stereographic projection from that is denoted Pn from the sphere without the north pole to R2, and the same geographic coordinates, but with respect to the projection from the sphere without the south pole. So now we can take the vector fields like this in local coordinates on so it's like a vector field in this open set, and now we want to write this vector field in other coordinates because we want to define also the vector in the north pole. So I can. So we know that.
Это сфера минус точка, да?
Да.
Просто обычно минус
Да,
точка в
set
другую
минус.
сторону.
Это коуш.
Да. So we know that
Если реализуете по одной точке, то ничего не меняется.
that these coordinates they are equal to this one. We just can calculate it
Yeah, I
explicitly.
think we did it.
Yeah, we did it last
once
time.
in,
It was like
Mhm.
the first problem, and the same is for the other coordinates. So now to compute these vector fields in other coordinates, we can write something like this. can calculate this derivative and this, and then express them in terms of not U and V, but U and V barred. So, and the result is like this. So we have so we expressed these vector fields in other coordinates, and so and this is we're doing the sphere without 2 points. But we can see that here, if we can define actually these vector fields in the North Pole, and it is actually equal to 0, because in local coordinates U and V barred, the coordinates of the North Pole are 0, 0. So now we can define the vector field on our sphere like this. So we take the pullback, it's called the pullback, of the vector field if P is not the North Pole, and it will be the pullback of if E is not the South Pole. So on the intersection of these two sets, everything is okay because of this formula. So yes, on the intersection, we know that this vector field equals this vector field. So this definition is actually correct, and also we can easily see that vector field in the North Pole is actually equal to 0. Yes, because the North Pole is 0, 0 in coordinates, in barred coordinates. So, and it is equal to this vector field not equal to 0 if P is not the North Pole. So I think that's all.
Did you think whether you can do something like this but require it at not to be 0 even at M?
So it's not 0 everywhere.
Yes, not 0 everywhere. Well, everybody knows that it cannot be done, right? Which is Hay-Raybaud theorem. But in principle, right, so again, the picture is that you have this constant vector field, right,
On a R2.
on a plane, and then you have this sphere. Well, rather, well, it's not this, like RP2, of course, is not. Well, okay, you have sphere, okay, no RP2 here, whatever. Yes. And then you have a small change on a plane, means you have small change right everywhere, right? And this goes to 0. And seems like if you would like to define something on the North Pole which is not 0, you have to make it not constant, but rather maybe larger and larger as you go to infinity. Right?
Yeah.
So I guess maybe abstraction is that you cannot do it kind of like you have different infinities, right, on the plane. And so you cannot do it consistent in all directions. That's the point. So I just thought maybe you can do something.
Такой код не может быть правильным.
Ну, может, он уж точно был.
Да.
Но его даже вещественная сфера такая.
Логично получается, что оно полагается ровно в трех.
Трех
Ой, в двух. Ну, потому что на лишней второй степени получается. Либо все будет.
Ну, сейчас.
Правильно я понимаю, что вопрос в том, что нет противоречий между темами и задачами.
Например, да, нет, вопрос в том, могу ли я, ну, если я потребую возможность, ну, теперь пойду в CP1, потребую возможность отребовать одну поле, то в скольких точках минимум должен обнулиться. Гипотеза двух была высказана. Я правильно понимаю? В северном южном полюсе.
Ну, там просто на лишней второй степени.
Да. Ну, в нуле понятно, как сейчас.
Не, ну я это в нуле тоже было.
И в бесконечности у меня тоже какой-то второй порядок. Да, тут как не хватило, почти будет обновляться. Нет, ну почему? А я констант